Eddy currents. A current is induced in a conducting coil when the magnetic flux through it changes. A solid conductor, such as a piece of metal, can also have currents induced within it when the magnetic flux changes. Here we have a piece of metal, and here we have a uniform magnetic field going into the screen, represented by these crosses. As the piece of metal moves into the magnetic field, the flux through the metal changes, and a current will be induced in the piece of metal. This is an eddy current. The piece of metal has gone from having no magnetic flux passing through it to an increasing amount of magnetic flux going into the piece of metal. You can verify using the right hand grip method that a current in this direction within the piece of metal will produce a magnetic field coming out of the screen, as required by Lenz's law. As the metal continues to pass through the uniform field, there is no change of flux, and so no eddy current. But as the metal now leaves the field, an eddy current in the opposite direction is set up, seeking to maintain the flux into the screen. Eddy currents can lead to energy losses due to heating in transformers. We don't need to cover transformers in depth, but they consist of an iron core round which we have a primary coil of wire which carries an alternating current. This produces a changing magnetic flux passing through the iron core. As the alternating current changes direction, so does the magnetic flux. We then have a changing magnetic flux through this secondary coil, and that then produces an alternating current out. The number of turns on the primary and secondary coil allow us to adjust the potential difference and current of the outgoing supply relative to the incoming supply. This changing magnetic flux in the iron core leads to eddy currents within the core. This can lead the iron core to heat up, which of course is an energy loss, reducing efficiency. By constructing the iron core from a series of laminated plates, like this, each separated by a thin insulating layer, it reduces the eddy currents within the core, and so means to less heating and a more efficient transformer. Eddy current or induction braking can be used on roller coasters. Here we have a block of aluminium which would be attached to a moving part, one of the cars in the roller coaster, and here a pair of permanent magnets which would be attached to the frame. As the aluminium block passes through the magnetic field, like this, the eddy currents within the block will produce heat from the kinetic energy. The forces which cause the slowing are produced by opposing magnetic fields. Lenz's law tells us that the magnetic field produced by the eddy current within the aluminium block will be in the opposite direction to the magnetic field due to the permanent magnets. The use of permanent magnets means no power is needed for braking, making the system safe in the event of a power cut. It also, however, means the braking power cannot be adjusted in use. Similar adjustable systems can be used using electromagnets in place of the permanent magnets. These are in use on some trains, for example. The induction hob uses eddy currents to heat food. The changing magnetic field produced by an alternating current in this solenoid produces eddy currents within the base of the pan. This heats the pan directly, which then heats the food. The hob itself only gains heat from the pan it's in contact with, making this a much safer and a more efficient system.